So we're going to have to start with the old exam number 2. This exam, our test is going to begin at redox and stop with Lewis structures. There's some redox questions in exam 2. Like number 5, oxidizers are electron poor. Is that true or false? True. That's correct. Oxidizers are electron poor. Methane is a neutral molecule that is best classified as electron rich. What do you guys say? That's also true. Let me know if you need further explanation or if you're good. It will just keep moving. But that's true. Okay, let me just fix that later. Element plus element combination, decomposition, single replacement, and combustion reactions are redox reactions. This is true. Eight. 8 is not redox. What kind of reaction is 8? Titanium 4 ions and sulfide ions will precipitate. That's metathesis. 9. The oxidation state on chlorine in ClO4 minus is what did you get? 7 plus 7 is correct. That's right. Why? Figure it out. Just go ahead and determine the oxidation states by the normal method. I showed you different ways to determine the oxidation state. I showed you 3 ways to determine the oxidation state. Okay, tell me one of the ways we can determine oxidation state. Yeah, based on Lewis structure we can. How can you determine the oxidation state based on Lewis structure? It's not the first way I showed you how to determine oxidation state. Well, we did the Lewis structure this yesterday. Did we do this one yesterday? So we have 2 choices. Now, formal charge and oxidation state are 2 different things. So these were the two Lewis structures I had up yesterday. Well, these two Lewis structures are going to have different arrangements of electrons, which deals with octet and formal charge. The octet and formal charge are different between these two structures. This one has an expanded octet. The formal charge is minimized. This one just has an octet with kind of high formal charges. But both of those structures have the exact same oxidation state. How do you determine oxidation state for the Lewis structure? That's the most recent way I showed you.
Formal charge.
Not formal charge. The oxidation state and formal charge are two different numbers.
Net charge.
Not the net charge. You make an assumption. What do you assume? Bonds are ionic. You assume the bonds are ionic, and when they're ionic, it's winner take all. So, in this case, chlorine versus oxygen, who wins? Oxygen. Oxygen gets all 8 electrons. Oxygen gets all 8 electrons. What is its oxidation state? Yeah, -2. All these oxygens are the same. -2, -2, -2. We can't compare oxidation states with formal charge. You can't compare them directly. The oxidation state is -2, however the formal charge is -1. And they say different things. It's like somebody asks you, you know, let's say you have a basket of apples and oranges mixed together. And somebody asks you, okay, give me the biggest apple, but they give you the biggest orange. You go, I didn't want the orange. But they say, well, the orange is bigger. But the same thing here, we can't compare the two numbers because they're comparing different things. You know, so this number and this number aren't related. They're related like apples and oranges. They're different. And we can't say, you know. But anyway, it leaves chlorine with how many electrons? Leaves chlorine with no electrons. Well, how many electrons was it supposed to have? 7. It contributed 7. So what it did was it contributed 7, and it got how many in return? None. So basically it lost all 7 electrons, which means it's +7. So the chlorine here is going to be +7. So that's one way. We could have done it using this structure too. Oxygen wins. Oxygen wins all the electrons, leaves chlorine with nothing, +7. Or we could have do it the original way. And so I said there are 3 ways. The first way I showed you was by doing this. We imagine each oxygen as being 2-. Each oxygen has its normal charge, like this, 2-. And this whole thing this is -8. -8 plus x is going to equal -1, the net charge. And so what is x? +7. So +7 -8 gives us -1 net charge. This is the way I originally did it. The second way I show you is this. I don't have this sheet with me. It's in the oxidation states supplement in the lab. But, you know, that's pretty much the same as the books. So we could take a look at the book. Unless, does somebody remember the books mentioned? A lot of people prefer the book method because it's in the book. Whereas these two methods are not in the book. And so a lot of people don't trust these two methods because they're not in the book. I much prefer something. So you could find it in the book. It's way out in chapter 19. And 19-3, this will take me there. We call them oxidation numbers. Oxidation number, oxidation states. All right, step one, the oxidation number of each atom in an elemental substance is 0. This is not an elemental substance, this is an ion. An elemental would be like hydrogen, helium, phosphorus. So skip that step. 2, the oxidation number of a monatomic, well this is not a monatomic, this is polyatomic. Skip this one. 3, the oxidation number of combined oxygen is -2. All right, so what we do is we say that each oxygen is -2 here, like this. And we have how many of those? 4, so that all together is going to give us -8. But -8 is not the oxidation number, -2 is the oxidation number. This oxidation number is not the net charge, the oxidation number is the charge on the individual atom. The oxidation number of combined hydrogen is +1. Well, we don't have combined hydrogen. What they mean by combined oxygen and combined hydrogen is this is some kind of compound or polyatomic ion. 5, in any molecular or ionic species, the sum of the oxidation numbers of all atoms in a molecule or polyatomic ion is equal to the net charge. And so here's where the net charge comes in. The net charge is -1, and we got to sum up all the oxidation numbers. So we have 4 at -2, so 4 times -2 plus 1 times x. 1 times x, because we only have 1 chlorine. 1 times x plus 4 times -2 is got to equal -1. So that means x plus -8 is equal to -1. And then solve for x. We solve for x by adding 8 to both sides. So x is equal to 8 minus 8, and then 8 plus a -1 gives us +7. So x is equal to +7. So those are the 3 methods that we use. We do it from the formula, we do it from the Lewis structure, or we do it by something like this. And the correct answer is +7. H plus can react with silver metal. Anybody figure this one out?
H minus reacts with metal.
No, there are H minus can be in metals. You know, for things that are easily oxidized, you can form H minus. Like for example, sodium plus hydrogen. Hydrogen's not a very good oxidizing agent. It's not even on the chart as an oxidizer. And so, but the potential's there to form sodium hydride. Sodium loses an electron, hydrogen gains it. So, that's not it. This one, H plus can react with silver metal. My thinking on this one is that You have the redox chart. Do you know how to use the redox chart? H plus. H plus is an oxidizer or reducer? Oxidizer. Can H plus oxidize lead? If H plus oxidizes lead, what forms? If H plus oxidizes lead, do you know what forms? Lead 2. Which one's stronger, H plus or lead 2? H plus, so we're going from stronger oxidizer to weaker oxidizer. Do you remember going through this? Did you guys commit this to memory already, or is it still shaky? And so if H plus oxidizes silver, what's produced? Silver ion. Which one's stronger, silver ion or H plus? Silver ion. So we're going from weaker to stronger. Going from weaker to stronger, is that driving force or redox? No. Based on the redox chart, it's no reaction. Is metathesis, 12 is isotopes, 13 isotopes, 14 atomic mass, can you do that? 15 mass number, 16 isotopes, 17 Avogadro's number, 18 atomic theory part 1, 19 20. CO2 can be combusted further to form CO3. True or false? Yeah. False? False. Yeah, this is false. Let's look further. 21. The oxidation state of chlorine varies from -1 to +5. It's false also. What does it vary from? Yeah, -1 to +7. What does carbon vary from? Minus what? 4 to +4. What's the oxidation state of carbon here? +6. 22. When aluminum is oxidized, AlO2 is a potential product. Jim? False? That's correct. This is false. Anybody know why? 22 is false. Okay.
Forms like Al2O3.
Yeah, it forms Al2O3. You're absolutely right. That's what it forms, but why can't we form AlO2?
There's no +4 aluminum.
Yeah, there's no +4 aluminum. Aluminum varies from +3 to minus something, -5. It only has 3 valence electrons. If it goes Al+4, we have to remove one from the inside shell, which is completely filled. It'd be neon. The reaction of F2 plus NaI fits the single replacement pattern. That's false. Why does it not fit the single replacement pattern? BX. It fits the A plus BX, that works. A plus BX works. But there's more to the pattern than just A plus BX. But the single replacement predicts A should be a. What's the role of A? Well, yeah, I know. It goes like AX plus B, but what do we call A? You know, what's the role of A? Uh-huh.
It's supposed to be like an element, but not a very top element, like H2 or something.
Well, it could be an element. We see elements all the time. For example, this one. This is a reaction we did. We actually did this one in lab. Magnesium solid or zinc solid plus 2 HCl's yields magnesium chloride plus H2. And so A and plus BX yields AX plus B, where A and B are elements. It doesn't matter if they're diatomic or monatomic or whatever, it doesn't matter. They're just elements. A and B are supposed to be elements. So this fits the pattern in the sense that A is an element. It's the element fluorine. It doesn't fit the pattern because there's more to the pattern than just A plus BX. There's defined roles.
A is supposed to be an oxidizer.
A is supposed to be an oxidizer. Is that the role that the director? This is the director of the chemical reaction, like a director of a movie. The director of a movie says, A, you're going to play the part of the oxidizer. Is that correct? A plays the part of the oxidizer. And then B plays the part of what? The reducer. And X plays the part spectator. So X is just a spectator, doesn't do anything. And so oxidizers do what? Oxidizers lose electrons or gain electrons? Oxidizers gain electrons. So if we go from magnesium to magnesium 2+, did that gain or did that lose? If we go from magnesium 0 to magnesium 2+, did it gain or lose? It lost. And so we need to reassign the roles. So let's reassign. What gained electrons? B or X? Well, B went from +1 to 0, and X went from -1 to -1, so X didn't change. So if B went from +1 to 0, then what must have happened? It gained electrons. So oxidizers gain electrons. That means that, which one's the species that gains electrons? B. For all single replacement reactions, A is not the oxidizer, A is the reducer, and B is the oxidizer. Why? Why? It's because that's the role the director of the chemical reaction gave each species. But you know, in this particular reaction, somebody might say that the director is blind. You know, the director must be blind because fluorine is the strongest. Fluorine is the strongest on the chart. Fluorine's the strongest oxidizer on the chart, but who got the role of oxidizer? Sodium ion. Sodium ion is the, well, anyway, sodium ion is 1, 2, 3, fourth weakest on the chart. And so the the director, fluorine might be screaming at the director because fluorine's saying that, why did sodium ion get the role of oxidizer? Fluorine's probably saying, I deserve the role of oxidizer, not sodium ion. But you say, no, I'm the director. I say which chemical plays which role. Are the chemicals going to listen to you even if you're the director? And you tell, okay, fluorine, you don't take electrons. You give up your electrons, and then you give them to sodium ion. No, the chemicals don't listen. The chemicals are just going to act. So anyway, that's why it doesn't fit. It doesn't fit. So this is one of the exceptions. So fluorine plus sodium iodide fits the single replacement pattern? No. 25. Gas formation is a driving force for redox. False. Gas formation is a driving force for metathesis in acid base, but not redox. What's the driving force for redox? Yeah, stronger to weaker oxidizer reducer. Okay, next. Lead, metal, and hydrochloric acid. What's the formula for lead? Yeah. This one you have two choices. One, you could, because this one looks to be single replacement, you could try single replacement. Or two, you could just use what method? Chart method. I can tell this one fits single replacement. How can I tell? It's very simple to tell if it fits or it doesn't fit. And that is, I just do a mental check. Do I have the best species representing each role? So A is the role, what role is A? The reducer. So I think, what are the reducers I have present? I have lead, I have chloride, and I have water. I have lead, chloride, and water. Which one is the most electron rich out of those? Lead, metals. So lead. And so I realize it's hard to, chloride's very stable, it's hard to burn the stuff. The same thing with water. Chloride and water are both awful reducers. Lead is way better. And so far this is going to work. But I have to look at the oxidizer. As far as oxidizers go, I have a choice. Lead, no, that's not an oxidizer. H+, yes. Chloride, is chloride a good oxidizer? No, chloride's an awful oxidizer. It's not even, because chloride has a filled shell. If chloride gains another electron, it has to go in the next higher energy shell, so it's going to make chloride with a 2- charge, which is very unstable. So chloride is not a good oxidizer. What about water? Is water a good oxidizer?
Yes.
It's not great. What's better, H+ or water? H+. And so the roles are properly assigned here. I could use single replacement. So if I did single replacement, this would form lead-2 chloride plus hydrogen gas, 2 two HCl's. And then lead versus hydrogen, which one's more reactive? Let's say if you have a box of lead or a tank of hydrogen, which one is more reactive? Say, get some old lead weights, fishing, or you have a tank of hydrogen. What would you use the tank of hydrogen for? Maybe fill up your Toyota Mirai. I saw one of those the other day filling up their hydrogen tank. Gets me thinking though, because hydrogen is pretty explosive stuff. They'll show in the movie somebody smoking a cigarette next to a gasoline tank, but they're going to have to change that. Now somebody's smoking a cigarette next to a hydrogen tank, the gas station. It's going to result in a much more massive explosion. So anyway, we don't even need the chart for this. We're going from stronger to weaker, or more active to lesser. Actually, no, are we? I don't know. We can consult the chart for that. Lead versus hydrogen. Looks like lead is more active, hydrogen is less active. So we're going from stronger reducing agent to weaker reducing agent, or more active element to less active element. Lithium's the most active down here, so lead's closer to lithium, hydrogen's a little farther. They're both pretty active though. Driving force. Alternatively, you don't have to do that. Alternatively, we could just use the chart method. We use the chart method, we inventory lead, H+, chloride, and water. The strongest reducing agent, lead. The strongest oxidizing agent, H+. Then write out the half reactions, Lead goes to lead 2+ plus 2 electrons. And then H+, 2H+ plus 2 electrons goes to hydrogen. Just combine them. Only thing we'd be missing is this. Once that redox reaction takes place, then there's going to be a metathesis reaction between lead ions and chloride ions. Lead and chloride like each other, no precipitate ions. So that's a second reaction that occurs. Acetic acid and calcium carbonate, that's metathesis. Barium nitrate, ammonium sulfate. Metathesis. Carbon is burned in air. Carbon is burned in air. Well, air has what in it? Oxygen. So if I burn carbon with oxygen, what forms? What do you think forms? CO2. So it's all balanced. Carbon solid, oxygen gas, CO2 gas. B, sodium metal and aqueous potassium chloride. Sodium metal, aqueous potassium chloride. Hey, this is A plus BX. Yeah. So what is A supposed to be? Reducer. Is sodium a good reducer? Yes. Sodium is the fourth most powerful reducer. This is good. This is quite good so far because A is supposed to be a reducer and sodium is a powerful reducer. Yeah, but what is B? B is the oxidizer, which is potassium ion. How good of an oxidizer is potassium ion? It's the second worst oxidizer. You know, potassium ion can only oxidize one thing on this chart. What is it? Lithium, the most powerful. If potassium ion tried to oxidize calcium, then it's no reaction, because potassium ion oxidizes calcium, well, forms calcium 2+. We're going from weaker to stronger, no reaction. If potassium ions try to oxidize sodium, is it going to be successful? No. So I already see there's no reaction there. So maybe I should write NR, but that would be a mistake. It would be a mistake because, you know, chloride's not an oxidizer, but there's one other species that I'm ignoring. Which one is that? Water. Because I know potassiums are not good oxidizers. Is water worse or is water better? Water's better. Where does water go? Yeah, right here. So if we have water, if water oxidizes sodium, then sodium ions form. And so we're going from stronger water to weaker sodium ions. So that works. I already see there's going to be a reaction here. It's not going to be with KCl, it's going to be with water. And so this one, the chart method does not work. Or not chart method. Chart method always works. You know, chart method always works. At least for predicting what we expect. You know, it works for predicting what we expect. Single replacement doesn't work here. Some people, when I was in Chem, I learned another single replacement pattern. The other single replacement pattern was like this. A plus Bx, where B is H plus and X is OH minus. And then what would you form? We'd form sodium hydroxide plus hydrogen. But that's knowing that water can react. So I could have done that. Here I just use the chart method. In fact, for all these you can use the chart method. What are the chemical properties of HNO3? So what are the redox properties of HNO3? HNO3 consists of H plus and nitrate. H plus is a oxidizer. And the nitrate in H plus is an oxidizer. An even stronger oxidizer. So nitrate in H plus is an oxidizer. Could it be a reducer? Could nitrate be a reducer? And an oxidizer? Or just an oxidizer? Nitrate can only be an oxidizer. Why? It cannot be a reducer. Nitrite can be both. Nitrite can be an oxidizer or a reducer. It can go either way. So why can nitrite go both ways, but nitrate can only go one way? I'm sorry? Yep. Well, some people might think it does. I mean, they're both -1 charge, -1, -1. But that's correct. Nitrate does not have any electrons to give. Why? Why? The oxygen is. What's the oxidation state of oxygen? -2. Doesn't oxygen have electrons to give? It does, but it doesn't want to. Right? Oxygen's happy at -2. You know, if you ever doubt that, think of water. Water, oxygen has a -2. And so, you know, good reducing agents are flammable, like metals, like ethanol. Electron rich, they're flammable. Is water flammable? No. And so it doesn't really give up these electrons. These electrons are stuck. So what doesn't have electrons to give? The N, yeah. What's the charge, the oxidation state on N? +5. So there are no electrons. It's already lost all those valence electrons. But nitrite, what is the oxidation state on nitrogen here? +3. So nitrite, nitrogen can give up electrons. It can give up 2 electrons potentially to form nitrogen +5, or it can gain electrons. So it can go either way. It's an oxidizer and a reducer. How it behaves depends on what you react it with. Whereas nitrate can only go one way. Oxidizer. That's it. Okay, 1. Electrons in the atom are in fixed orbits. True or false? False. 2. Hydrogen lamps are expected to emit white light similar to incandescent tungsten light bulbs. False. They predicted that hydrogen lamps were going to emit what kind of light? You know, what is the biggest hydrogen lamp you can think of? The sun. The sun emits what color light? Well, the sun, this is a trick question. The sun emits all colors of light. When you combine all colors of light, it looks white. So the sun is a hydrogen lamp, emits white light. And so this is actually true. They expected hydrogen to emit white light like the sun. Did it? No. 3. The 211 NLM orbital is forbidden. False. It's allowed. That's a 2p orbital. 4. Quantum numbers originate from the Bohr equation. Yeah. Well, actually, one quantum number comes from the Bohr equation. That's n. But L, M, S don't. Where do those come from? Schrodinger equation. Quantum mechanics.
Some would be false.
It's false. Quantum numbers come from the Schrodinger equation, not the Bohr. Five. 6,563 for N. L is 452 and M is 0 is forbidden. That's false. That's actually allowed. Well, if we have 6,563, the maximum L value is going to be 6,562. So it's going to be all L values, 0 to 6,562 are allowed. And then if L is 452, then any integer from -452 to +452 is allowed for M. So that's false. That's allowed. 6, 7, 1, -1 is a p orbital. False. Well, the middle number is L. So L equals 0 is what we call an s orbital. L equals 0 is an s orbital. L equals 1 is what type of orbital? It's a p orbital. And so this is L equals 1. That's true. We have three p orbitals. The three p orbitals are this. We're going to have the 7, 1, minus 1, the 7, 1, and the 7, 1, 1. Those are our three 7p orbitals. Seven. K, potassium is harder to ionize than sodium because of its many protons. Well, let's take the first part. What's harder to ionize, sodium or potassium? Is that true? Potassium is harder to ionize than sodium, or is that false? Well, what's largely, what factor largely determines ionization energy? Electronegativity, yes, but what factor were we talking about earlier in that chapter? Shells, yeah, it's one factor. The size, yeah. So what's bigger, sodium or potassium? Potassium's bigger. Yeah. So potassium should be easier to ionize than sodium. So the first part of this is false. Potassium should be easier to ionize. It's true it has many protons. Let's also get another shell. 8. How many orbitals are there in the L equals 6 sublevel? Thirteen, correct. You guys know how to figure that out? Minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6 is altogether 13. 13 values. There's an easy way to figure it out. When L, let's say L equals 6, then we have minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. And so this is 6 values here, this is 6 values here, and this is 1. And so the number is 2L plus 1. So if L equals 6, there's 13. If L equals 50, how many M values are there? 101. The number of valence electrons for argon 4s2 3d8 is 8. Eight is not correct. It is, well, valence electrons are the highest N. And so this is actually going to be 2 valence electrons are it. 2. Okay, we'll come back to that, but it's the valence electrons are the highest N electrons. Some of these D electrons, which are inner electrons, can react, but the highest N would be 2. So plus 2 is a common charge, and then we might lose 1, 2, 3 of the D electrons, but probably not all of them. Okay. All right, so let's take a break now, and then we'll start up again after our break.